So really today we're going to have 5 goals. When you have a rational function, there's really 5 things you want to consider or find. We're going to find vertical asymptotes. We're going to find holes in our graph, and we'll talk about the difference between a vertical asymptote and a hole. Those are called points of discontinuity. So we'll kind of use some of these words interchangeably, but if I say a point of discontinuity, I'm either talking about a vertical asymptote or a hole. We're also going to find horizontal asymptotes. And then lastly, we're going to find x-intercepts, and we're going to find y-intercepts of our functions. Just a little bit of reminder, this hopefully isn't, it should be a little bit of review because this works for every function. To find an x-intercept, basically you plug in 0 for y and solve. To find your y-intercept, you plug 0 in for x and solve. But this is big picture. This is what our goals are for today. And it's like I said, I'm throwing a lot of information at you today. But like I said, we'll take time to kind of break these down more. So right now, I'm just going to kind of just throw a ton of it at you, and then we'll start processing it hopefully this week and maybe a little bit next week. So 8.3, rational functions. Remember, a rational function is any function that can be written in the form of f of x equals p over x over q of x. Basically, you have a fraction. That's what a rational number. A rational number is a number where you can write it as a fraction. So like 1/2 is a rational number, but pi is not a rational number because you can't write it as like a number over a number or a fraction. One thing to keep in mind is that q of x can't equal 0, or you can't have 0 on our denominator because you can't divide by 0. A little bit of vocabulary, a continuous graph. I don't know if you've heard of this before, but basically a continuous graph is a graph where you can draw it without lifting your pencil. So like, for example, if I drew like a line, that's continuous because I can draw it without lifting my pencil ever. But if I'm drawing a graph and it's got like 2 separate parts and I got to pick up my pencil or I got to stop, there's like a gap in it, that's a discontinuous graph. That means there's a hole, or there's going to be some kind of asymptote. There's going to be something that breaks your graph into like 2 separate parts. Okay. So I don't know if you're familiar with continuous or discontinuous graphs, but that's what those words mean. So what we're going to start with today, we're going to start with points of discontinuity. This is where you have an x-coordinate of a point where you have to pick up your pencil. And this can show up as either being a hole or a vertical asymptote. These are 2 types of points of discontinuity. So let's start with this function here. And I kind of copied and pasted these pictures in just because I knew if I tried to draw them on my own. But if you graph this function, if you ask yourself, what can't I plug into the function 1 over x minus 3? What would make the bottom equal 0? Well, that would be positive 3. So I have a point of discontinuity at x equals 3. And we're going to talk about, since it's not removable, if I graph this function, it would look like this. I would have a vertical asymptote at x equals 3. Let's look at if we have a hole. So one thing you're going to see when you have these rational functions, you want to use some of our skills with factoring to see if you can simplify this at all. So if you remember x squared minus 16, does anyone know what that would factor down into? It's a difference of squares. Do you recognize that? Like, what would x squared minus 16 factor down to? Like, what would it factor? Like, how would we factor that? So we could rewrite x squared minus 16 as x plus 4, x minus 4. Because if you remember, that's like one of those special cases. It's a difference of squares. So do you see how the x plus 4s would cancel? And you would get that this equals x minus 4. The problem is you still, like, even though that cancels, you still can't plug negative 4 into this function. If you plug negative 4 in, you're still going to get an undefined value, right? Even though it canceled, like, I mean, you could plug negative 4 into x minus 4, but you still couldn't plug it into that original equation. So if this is called a removable point of discontinuity, and what it's going to look like if you graph this, like you would just graph the line x minus 4, but you're going to have a hole at -4. So if you have someone that cancels out on the bottom of your fraction, it's going to create like a single hole or a single point. And once you get your, like, since your x can't equal -4, if you plug it into this new function here, that will give you your y value. So that's why this hole's at -4, -8. So when you actually find a hole to get like your whole point of your hole, you plug that x value into your simplified form. But basically, if you have something that cancels out from the bottom of your fraction, that's going to create a hole. And we'll look at these some more. So I'm just kind of like, it's a rough kind of brush over start right now. But if you graph this function, it would look like what I have here, like where you have just a single hole. So when you have a hole, it's just a single point where your graph isn't defined. And sorry, I know this is sloppy. I did post like a key to these notes that's a little bit neater than my like chicken scratch. So just, you might want to look at those on Google Classroom. The next thing we're going to be look at is a vertical asymptote. A vertical asymptote is any values that you can't remove from the bottom of your fraction. So if you simplified this, also using the difference of squares, I mean, this would simplify, the bottom would be x plus 2, x minus 2. And since you can't remove those, like you can't cancel it out with like a binomial on the top, your function wouldn't be able to equal -2 because that would make the first binomial equal 0, and your function can't equal +2 as well. Since you couldn't remove those create vertical asymptotes. So if you can't remove it, you're going to have a vertical asymptote at those points. And don't worry about the graph. I know that graph looks kind of crazy. We're just focused at like, just that's where your asymptotes would be. Any questions so far? So first big idea so far is if you have a value on the bottom of your fraction that cancels out, what would make that undefined is going to create a hole. If you have something on your denominator that can't be canceled, that's going to create a vertical asymptote. So in terms of finding holes or vertical asymptotes, you're going to be looking at what would make the bottom of your fraction equal 0, or what you can't plug into your function. Check so far. So those are, and if you remember like the 5 things, these are the first 2 big concepts, like our goals for this unit. So let's look at some examples, and we're just going to be really focused on whether finding holes or vertical asymptotes, okay? So this function here, what can't I plug into this function, 1 over x squared? Like what would be a point of discontinuity on the bottom there? Like what can't you plug into 1 over x squared? 0, right? Because you can't have 1 over 0, right? If you divide by 0, bad, can't do it. If you put that in your calculator, any number divided by 0, it's going to give you either domain error or an error. You can't divide by 0. We can talk maybe more in the future why. I mean, it really just doesn't make sense. How many times does 0 go into something? Well, it's a question of infinite, or, I mean, there's different things. Maybe that's something we can look more into, but for now, just can't divide by 0. And you can't remove this. It's not like I can cancel out that x squared on the bottom. So this is non-removable. So we're going to have a vertical asymptote, and I'm just going to abbreviate that VA at x equals 0. So if I graph this, and don't worry about my actual sketch, you can make a table of value or you could use a graphing calculator, but you're going to see if you graph this, it would kind of make those branches we saw yesterday, but it would look kind of like this. But don't worry about like the actual sketch. Really right now, we're just really interested. Right now, there would be a vertical asymptote at x equals 0. Okay. We'll talk more like big picture when we're actually graphing these from scratch. But right now, we're just focused on either finding holes or vertical asymptotes. Okay. I'll keep this up when we look at the next one. I'll try. Example 2. What can't we plug into the bottom of this function? What would make the bottom equal 0, or what would make this undefined? Positive 2. So x can't equal positive 2. But be careful, in this problem, you can remove that. Like it would cancel out. Like this really would just equal x plus 1. So that's called removable. So since that's removable, we're going to have a hole at x equals 2. But usually when you find a hole, it's a point. So you got to find the y value. To find the y value of this hole, you're going to plug this x value into your simplified function here. So if you plugged in 2 for x, you would get 2 plus 1 is 3. So if we graph this function, we're going to graph this x plus 1 line. Like so, just like if you were graphing that line, you would start up at 1. And your slope's going, I mean, we're doing a really rough sketch, but your slope would just be 1 over 1, right? So you would just sketch your line. So it might look something, I mean, I know this is a really rough sketch. It would look something kind of like this. Let's see if I can draw this a little bit better. But at 2, 3, it's going to have like a hole. So you kind of just leave like an open circle just at that single point. So sorry, I'm trying my best to sketch this. But so it would basically be the line x plus 1, but you would have an open circle at the point 2, 3. And that's called a hole. Because like if you were graphing this function, basically you pick up your pencil at that spot, start drawing it again. So if it's removable, you're going to make a hole. If it's not removable, you're going to have a vertical asymptote. Okay. Example 3, similar idea to example 2, you still couldn't have x equals 2, right? Because that would make the bottom equal 0. But is that removable? Can you cancel out that x minus 2? No, like you can't, like you always want to check, can you factor out the top, or is there anything you can do to simplify the top? But there's nothing you can do with x plus 1. So since this is not removable, I can't cancel out that x minus 2. That's going to be a vertical asymptote at x equals 2. So you would have like that dashed or dotted line. And we'll talk about this more. Oh, they didn't really sketch it all the way. Because we haven't really talked about horizontal asymptotes. They do more in the notes here than I do. I'm just going to tell you, we'll talk about how to find this. I'm just going to tell you there's a horizontal asymptote at y equals 1. We'll see later in the notes, we'll talk about horizontal asymptotes. So I'm just going to tell you this, because if not, you really couldn't sketch this very well. But you would have a horizontal asymptote. And we like we've shown, we could plot some points. But basically, if you graphed it, it would look kind of like this. If I'm losing you a little bit, don't worry. It's with these notes, it's kind of strange that they have you graph something like this without talking about horizontal asymptote yet. So that green dotted line, I'm just telling you that's where it is. We'll talk more about how to find that in a second. That's what the rough sketch would look like. But really, right, like I said, right now, we're really just focused on, like, my goal with these previous questions is, do we understand how to find if we're going to have a hole or a vertical asymptote? So let's look at a few more examples. We're not going to actually graph these. We're just going to find some points. And then we're also going to maybe practice finding x and y intercepts, because that's something we haven't done yet. So in this, I'll do this first one with you. So they want us to find any points of discontinuity. And then we want to figure out if they're removable or non-removable. And then we'll state the domain. They ask for a few things. But so let's just start with simplifying this. So it's a difference of squares. So remember, you can write that like this. So what would our points of discontinuity be? Like, what can't we plug into the bottom of this fraction? And since these are non-removable, so these are both non-renewable, or not non-renewable, removable, if I could speak. So since they're non-removable, what that means is, remember, those are going to be vertical asymptotes. So sorry, I know I'm writing this a little bit sloppy. I'm not going to. Let me rewrite this a little bit smaller just because there's other things we need to do. So since they're non-removable, that means we're going to have a vertical asymptote at both of these values. Sorry, that's supposed to be an equal sign. It kind of looks like a not equals. Okay, so since you can't get rid of those, they ask us to state the domain, find the x and y intercept. So to find your x, and so well, I'm not really too worried about the domain for right now. Let's look at the x and y intercept. So to find an x intercept, if you remember, an x intercept is always going to be 0. Wait, no, that's backwards. That's the y intercept. It's going to be something comma 0. Basically, it's going to be on the x-axis. So if you look at this original function, you plug in 0. Well, actually, wait a minute. Because is it based on the domain? Because this one's actually not going to have any intercepts. So I'm trying to think if there's a better way to explain this. Because if you did plug in 0 for y, you would have this. I guess this is more of a thought. I don't know if this one's kind of a strange one. It's more of a thought. Is there anything you could plug in x that would make this equal 0? Now, this 1 over something is never going to equal 0, right? So this one's actually not going to have an x-intercept. This one's a little bit, it's more of almost like a thought part. Even if you did multiply it, basically if you multiplied both sides by the denominator here, you're just going to get 0 equals 1. So that's undefined. And similar idea, if you try to find your y-intercept, if you remember, your y-intercept is always going to be 0 comma something. So you plug in 0 for x. So if you had y equals 1 over 0 minus 4, oh, there should be a y-intercept. Wonder if this key is wrong, because the y-intercept would be negative 1/4. But I could be mistaken. I'd have to graph this and see, but I think that should be the y-intercept. If you plug 0 in for x, that's what you would get. So the y-intercept is usually easier to find than the x-intercept. So I'll actually double check this key because I'm curious to see if it's correct about the intercept there. I agree that there's no x-intercept though. So for question B, and then maybe I'll have you try maybe question C. So the first thing you want to do with these problems is always simplify your numerator and your denominator. Like if you can factor it out, you always want to do that. So the top is also a difference of squares. So remember, that would really, x squared minus 1, you could really rewrite that as x plus 1, x minus 1. And then the bottom, unfortunately, we really can't do anything with that. Like there's no real, there's nothing where it's like a sum of squares. There's no fancy way, like you Google sum of squares factor, there's nothing's really going to come up. Like maybe there's like a really special case, but there's nothing you can do to simplify x squared plus 1. So unfortunately, nothing's going to cancel out. Is there anything you can plug into the bottom that would make this equal 0 though? Just here's like a quick test you can do. I always like plug in a negative number. If I plug in, say, -2, that would be positive 4 plus 1, that's 5. That's okay. I always check 0. If I plug in 0, 0 squared plus 1, that's 1. That's okay. And then I plug in like a positive 5 squared, 25 plus 1. That's okay. So my gauge is there's nothing that I could plug into this that would be a problem, because an x squared is going to make anything always a positive. So since you're squaring a number, it's always going to be a positive plus 1. That's not going to give you any issues. So there's no way that's ever going to equal 0 with real numbers. And if you solve this equation, like you could always just even set it equal to 0 to solve, you're going to get x squared equals -1. So So really it would be I plus or minus I, but we're just focusing on real numbers, not imaginary numbers for what we're doing. So since there is no values that make the denominator equal to 0, this would actually be a problem where there's no points of discontinuity. So there would be no vertical asymptotes or holes. So, oops. So there wouldn't be any of those cases because there's not anything that gives me a problem on the bottom that can be removed or not removed. There's just no problems on the bottom. So there's no vertical asymptotes or holes. To find our x-intercepts, maybe there's an easier way. I might have to reapproach how to find the x-intercepts and y-intercept because I almost think it might be easier than I'm making it for the x-intercepts. It might just be what makes the top equal 0. I might be wrong about that. Okay, let's start with the y. To find your y-intercept though, you're just going to plug in 0 for x. So to get your y-intercept, the y-intercept's easy to find. Just plug in 0 for x. So if I plug 0 on the top, like this would be 1 for the first parentheses. This would be -1. So if you multiply that together, you would get -1 on top. If you plug 0 on the bottom, you're just going to get 1. So your y-intercept would be at 0, -1. So to get your x-intercepts, let me take a second to pause. I want to think. So sorry, I just wanted to think if you are watching this video later. So to find your x-intercept, you're going to plug in 0 for y. So if you did that, you would have this. Basically, if you multiply this bottom to both sides, basically it's just going to cancel out. Like if you multiply it by 0, it just still going to equal 0. So essentially, we're just going to get 0 equals x squared minus 1. If you add the 1 to the other side, you'd have 1 equals x squared. If you solve this, you're basically going to get plus or minus 1 equals x. So since we actually got 2 answers, that means we're going to have 2 x-intercepts. So we'd have one at +1, 0, and we'd have one at -1, 0. And to be honest with you guys, I mean, it is nice. I mean, you are like, we'll see some of the sections in Delta Math are going to have you find these, but honestly, it's not always the biggest deal to get your x-intercepts and y-intercepts because a lot of times when you're actually graphing these, you're probably going to have a graphing calculator where you can get a set of points pretty easily. I'll show you guys maybe even later. Like I said, I'm throwing a million things at you, I feel like today. But I'll show you, there is like a way with a graphing calculator, you can find x and y intercepts using your calculator. Like there's like a thing you have to do on it. So maybe I'll show you that for this. It might be helpful if you're having trouble with this. But this is how you would do it algebraically. Basically, to find your x-intercepts, you plug in 0 for your y, solve, see what you get. To find your y-intercept, you plug in 0 for x, see what you get. So the y-intercept usually for most of how these functions are set up is usually the easier of the two. The x-intercepts, you're going to have to do a little bit of solving. But let's look at one more of these. So like I said, you always want to simplify if possible. So if you factor that trinomial, like what multiplies to 2 and adds up to 3, you could rewrite that as x plus 2, x plus 1. So you're going to see that your x plus 1s cancel. So if you ask yourself, what can't your function equal? Well, your function couldn't equal -1, and your function couldn't equal -2. So, but since if you look, the -1 was removable. So you're going to have a hole at -1. And remember, to find your y value of your hole, you're going to plug it into your simplified version. So if you plug -1 into this, you would have 1/1 because -1 plus 2 on the bottom. So it would just be 1. And then since you have a non-removable undefined value at -2, that's just going to be a vertical asymptote at x equals -2 because you can't remove that x plus 2 on the bottom. To find our x and y intercepts, I'm going to do the y-intercept first because, like I said, that's usually the easier of the two. Basically, for the y-intercept, you just plug 0 into this function, and you're going to look at the simplified one. So 1 over 0 plus 2, that would just be 1/2. Like, and you always want to plug it into the simplified version, but you're plugging 0 for x. To get your x-intercepts, you're going to plug in 0 for y. So you'd have 0 equals 1 over x plus 2. If you start solving this, though, you're going to see it's undefined. Like if you multiply both sides by the x plus 2, you're just going to get 0 equals 1. So this one's actually not going to have any x-intercepts. Eventually, when we talk about some of our horizontal asymptotes too, that might even kind of help you see that before you do this algebra. So we'll talk. I think the x-intercepts and the y-intercepts might be something that gives some people some trouble. So I'll try and think of some tips. There might be some way to save you some time with this. Just double check. Okay. So let's just take a second to breathe because like I said, I know there's like, I feel like I'm just throwing so much at you right now. I'm probably losing you. You're probably like, what the hell is going on? So breathe. But like I said, just to kind of like take a step back. Basically, you're simplifying these. You get something that cancels out. You're going to create a hole. And remember, when you find your hole, it's going to be an ordered pair. So you got to plug that x value into your simplified function to get the y value. If you have something that can't be removed from your denominator that causes an issue, those are going to create vertical asymptotes. Then we talked a little bit about how to find x and y intercepts. To find an x-intercept, you plug in 0 for y, see if you can solve it. To find a y-intercept, you plug in 0 for x, see what you get. Like I said, I'll show you some ways you can use a calculator to kind of help you with those maybe in the future. I'm going to skip this section here. Well, I mean, I can do it really quickly. I mean, these are really quick, but they're literally just asking you to find vertical asymptotes. That's it. So you just want to make sure nothing can be removed. So this first one would have 2 vertical asymptotes. You'd have one at +1, and you'd have one at -3, because you can't remove those from the bottom. For graph B, since the x minus 2's cancel, your only vertical asymptote would be at x equals -3. You would actually have a hole at +2, but they don't ask. They're literally just asking for vertical asymptotes. For this one, if you simplify, I need to write smaller. It would be x plus 1, x minus 1. So since that cancels, you literally don't have anything. You don't have any vertical asymptotes. You would have a hole at -1, but this one would actually have no vertical asymptotes. So this section, just keep in mind, they're just asking for vertical asymptotes, so we're not worried about anything else. So since there wouldn't be anything on the bottom there that can't be removed, C would have no vertical asymptotes. So if you remember our first 5 things, like our 5 goals for today, we said finding vertical asymptotes, we said finding holes, and we talked a little bit about x and y intercepts. The one thing we haven't touched at all so far is horizontal asymptotes. So that's what we're going to look at next. Okay, horizontal asymptotes are kind of a weird, kind of a stranger one to kind of think about. Basically, you're going to look at the degrees of your numerator and your denominator. If you remember, the degree of a function is basically your highest power. So if you had like an x squared, your degree is 2. If you had x to the 3rd power, your degree is 3. So keep in mind, we're talking about degree, we're talking about the highest power of the variable in each one of the functions. So, so one thing we're going to see is we're always going to compare the degree of our numerator to the degree of our denominator. So if our numerator has a smaller degree than our bottom, you're always going to have a y-intercept at 0. So for example, that might look something like this. If you had x over x squared, your top has a smaller power than the bottom, you're going to have a y-intercept, a horizontal asymptote at y equals 0. If your numerator has a higher power than your denominator, you don't have any horizontal asymptotes. So for example, if it was the reverse, you had like x squared on top, like a degree 2 over a degree 1, you would have no horizontal asymptotes. And then where it gets a little bit, sometimes this is maybe like the case you got to be a little bit careful about is if you have the same degrees. So let's say you had 5x squared over 3x squared, for example. If you have the same degree, you look at the coefficients. So if this was actually like what we were looking at, my horizontal asymptote would be at 5 over 3. Like, for example, if this was my example, I'd have 1 at 5 over 3. There's other types, so this is just for horizontal asymptotes. We'll see if we do it this year, or you might in the future. So far we've only looked at vertical and horizontal. You actually can have a diagonal asymptote. It's called an oblique asymptote. Maybe that's something we'll look at if we're feeling ambitious later. But let's just look at some functions, see if we can find the horizontal asymptote. So for this first one, you always want to look at the degrees. So the first thing I notice in part A is that I have the same degree on the top and the bottom. I both have like x up to the first power. So since they're the same degree, I look at the coefficients of just the x part, like my highest powered part. So I would have a horizontal asymptote at y equals -8 over 2, which you could simplify, be -4. For question B, I see that my degree up top is smaller than my degree on the bottom. So I always, like, even myself, I mean, maybe there's a better way to memorize this. I always have to kind of look at this chart, I feel like, when I'm doing things like this. But since my numerator is smaller than my denominator in terms of degree, I just have a y-intercept at y equals 0. And then for question C, my numerator has a higher power than the bottom, so that just means I don't have a horizontal asymptote. But this table here, honestly, you might want to write this down or even take a picture of this, because this is something I always have to look back at, like, at least myself. Maybe if I find someone that's a way to help you memorize or remember these, but like even when I'm teaching this, I find I have to kind of reference this table. I don't know why. But maybe if someone's got a clever way. So I know I've thrown a crap ton at you. I'm sure there's some people in the Zoom, you're like zoned out. You're like, I'll try to figure it out on my own later. I'll watch the Delta Math videos. I don't blame you. Let's look at one of these. We're just going to look at a problem and we're going to see if we can do all 5 of the things we've talked about today. So we're going to start with vertical asymptotes, holes, horizontal asymptotes. I usually save the x and y intercepts for last when I'm doing these. So let's start. Well, first off, you want to always, I guess, before we even start listing any information, you always want to start by simplifying your function. So I mean, the top you can't do anything with, but the bottom, what would multiply to -6 and add up to 1? Well, that would be x plus 3, x minus 2. So right away, I see I can cancel that. We'll do it. Hopefully I don't get in the way of my graph later. But this would really simplify to 1 over x minus 2. So first off, for my vertical asymptote, I can't get rid of that x minus 2. So I would have a vertical asymptote at x equals 2. Because I can't have 2 on the bottom for that 1 over x minus 2 part, right? Since I canceled out the x plus 3 part, I would have a hole at x equals 3. Like I'd have a hole at 3. But remember, a hole's an ordered point. So to find the y value, I plug it into my simplified version here. So like 1 over 3 minus 2, that would just be 1 over 1. So 1. Then I'm going to do my horizontal asymptote. So if I look, my degree on top is smaller than my degree on the bottom. So if I recall, that means I don't have any, right? Oh, nope, I'm wrong. It's y equals 0. See, that's why I got to look at the table. But if you look at that table, if your degree up top is smaller than your bottom, you have a horizontal asymptote at y equals 0. Okay? And then I guess we'll find an x and y intercept. So your y-intercept, like I said, I'm going to do this one because it's always easier. It's 0 for your x value. You're just going to plug in 0 into this function here for x. So 1 over 0 minus 2, that would be -1/2. The x-intercept, because keep in mind this is equal to y. So if I plug in, it's going to be, remember your x-intercept is going to be something comma 0. So if I plug in 0 for y in this function, like I don't know if you see this, but basically if you multiply this across, like you're still just going to have 0 equals 1. That's like undefined. So this one's not going to have any x-intercepts. And if this is something we have trouble with, like I said, we can look at this some more later. So we found our 5 big pieces of information. Now to kind of get a sketch of our graph. So I like to always draw in my vertical asymptote. So that would be like this. I have a horizontal asymptote at 0. And then I have a hole at 3, 1. So I like to even draw that in just so I don't forget. And you can either make an XY table by hand, but honestly, my advice is if you have a graphing calculator or like an app, you always want to graph the simplified version. So if you remember, it was just 1 divided by, I believe it was x minus 2. Let me just double check that. Oops. Okay, and then just remember when you plug it in your calculator, though, notice how when I did 1 divided by, I put parentheses. You want to put the whole denominator in parentheses because your calculator won't understand it. You're dividing by the whole thing if you don't do that. So if you graph, basically, you could go to second graph to get some points. You could write down some of these points. So for example, I see a nice point at 1, -1. That's popping out to me. I see another point at 3, 1. So I see, if you see where the area is, that's where your vertical asymptote was. So I just want at least 1 or 2 points on both sides. So I'm just going to use, I just saw a couple nice points. So if I go back to this, one of the points I had was at 3, 1. Keep in mind, your graphing calculator is not going to tell you that's a hole. But basically, if I kind of looked at my picture, like I know like this branch kind of goes like this. And then I had another point at 1, -1. So that's here. So I'm going to have a, like, it's going to kind of look like this. And we're just getting a really rough sketch. But does that kind of make sense? So you can use the calculator to like get a couple points or even just see what it looks like in your calculator, where your branches are going to go. I mean, I don't need your graph to be super precise by any means because it's going to be contained between those asymptotes. So what you're sketching is actually going to be pretty good anyways. I guess I could have, I kind of forgot. If you have X and Y intercepts, obviously you can plot those points. So I could have put a point at 0, -1/2. But if you don't have any intercepts, you're probably going to have to get more points anyways. But remember, if you do find X and Y intercepts, those are points you can definitely use. So that's kind of this idea altogether. We don't have enough time to do the last question, but this is where we're going. Like this is what I would like you to do on your next quiz. If I give you a question like this, I would like you to find these 5 pieces of information. And I'm sure so right now, some of you guys are like, so if I don't even know what you said today, like I don't even know like how to find my name on the paper right now. But I'm sure some of you guys, it'll start clicking. But this is what we'll be practicing.